Welcome to the second video lecture in week 5 of discrete mathematics. We have been looking at the proof technique called induction. Till now, we have seen quite a number of different proof techniques, namely constructive proofs, proof by contradiction, proof by contrapositive, counterexample and induction. Last week and this week, we have been looking at this induction. Now, what is induction? The main idea is that sometimes the set of assumptions can be split up into finite but countably many subsets. So that in turn means that the problem, which is A implies B, can be split up into and of infinitely many problems. Now, each of these subproblems are usually indexed by some parameter of the input, and we like the problem A implies B as P1 and P2 and so on till P infinity. Now, this problem A implies B thus becomes this problem. For all k greater than or equal to 1, proves that Pk is true. There is of course one obvious way of solving them. Namely, first prove P1 is true, then prove P2 is true, then prove P3 is true, and so on and so forth. Unfortunately, since there are infinitely many subproblems, one cannot expect to solve all the subproblems. So we have to come up with some cleverer way of solving the infinite cases in one go. The idea is, first prove P1 is true. And assuming that you can prove Pk is true, prove that Pk plus 1 is true. So it's like if I write down all the integers or natural numbers 1, 2, 3, 4, 5 and so on in this number line. This says that first proof P1 is true, so I have proved that P1 is true. Now the second statement, this red line, says that if I know Pk is true, then I know Pk plus 1 is true. Since I know P1 is true, therefore P1 plus 1, which is P2, is true. Since I know P2 is true, therefore I know P3 is true. Since I know P3 is true, so I know P4 is true. So this way, the idea is that I will be able to prove anything. For example, if you tell me, can you prove P10 is true? Yes, I keep on continuing like this. P1 is true, therefore P2 is true, therefore P3 is true, therefore P4 is true, therefore P5 is true, therefore P6 is true, therefore P7 is true, therefore P8 is true, therefore P9 is true, and therefore P10 is true. So this way, I will be able to prove that for all n greater than or equal to 1, the problem Pn is true and hence proved. Unfortunately, this proof technique doesn't follow from the usual rules of propositional logic. We need a particular axiom for it, which says that this proof technique is actually correct. We call this one the principle of mathematical induction, and this is what it says, that if you solve it accordingly, then if you can solve P1 is true, and then for all k, if you can solve Pk is true implies Pk plus 1 is true, then you end up proving that Pk is true for all k greater than or equal to 1. So this is a very useful proof technique to have. We have already seen quite a number of applications of this proof technique, and we will keep on seeing more and more interesting proof techniques using interesting problem solving using this proof technique. So this mathematical induction has different versions of it, and we might be interested in applying one of the other for them. The version 1 is of course what we just now showed, which is that if we have to prove that for all k greater than or equal to 1, pk is true, the idea is prove p1 is true, then assuming pk is true, prove pk plus 1 is true. And if you can solve that, then we will solve the whole problem. The version 2 is a similar version, except that we shift the base case. So if we have to prove that a statement is true for k greater than or equal to r, we start with the base case of PR is true, then assuming the induction hypothesis, we prove that pk plus 1 is true, and that will help us to solve all the problems. There is a version 3 which also solves the same problem, but we have a different inductive state and hence a different base case. So here we have to again prove that for all k greater than or equal to r, pk is true. The way to prove it is, first prove pr and pr plus 1 is true, and then assuming that pk is true, prove that pk plus 2 is true. Again I repeat, all the versions just ensures that if here is r, so all the integers greater than r are covered by this step, if I follow this step. So this says that, okay, let me start with pr is true and pr plus 1 is true, this is the base case. The inductive states that if k is true, then k plus 2 is true. So r is true, therefore r plus 2 is true. If r plus 1 is true, therefore r plus 3 is true. Since now r plus 2 is true, therefore r plus 4 is true, and so on and so forth. We can again, you can see, ensure that all the points greater than r are covered by this step. Now one might of course ask why to use the different versions. It all depends upon the problem. For some problems, proving pk plus 1 is true, assuming pk is true, is easy, whereas for some problem, proving pk plus 2 is true, assuming pk is true, is again easy. So different problems gives us different easiness of proving a particular step, and depending on the inductive step that we can solve easily, our base case changes, our version that we apply of the induction, mathematical induction changes. So this was the version 3, and the version 3 of course says that if you can prove that k is true and k plus 2 is true with the base case of pr and pr plus 1, we have the problem is true for all n greater than or equal to r. In the last video lecture, we saw another version. The problem is again the same. The base case are all the same, except that in the induction hypothesis, we have to assume both pk and pk plus 1 is true, and assuming that we have to prove pk plus 2 is true. Again, the reason is that there are problems, as we saw in the last class or last video lecture, that proving that pk is true requires us to assume something about pk and pk plus 1 is true. So there are problems where this particular inductive step is easy to prove, and then accordingly you choose the correct version of mathematical induction. Now there can be many other versions that you can think of. Problems, for every problem there can be a different version required, and as long as you ensure that the basic concept that all the points are covered, you can apply that induction hypothesis or in the mathematical induction logic. Now, in all of them, we have assumed that we induct on k, in the sense that this k was increasing, so we kind of kept on solving for induct on k. That means we prove for k or k plus 1, then you prove k plus 2, or k, then it implies k plus 1, and so on. But sometimes we might have problems where there are multiple variables. So there can be multiple parameters. In that case, what parameter or which parameter do you induct on? In fact, can you induct on multiple parameters at the same time? So let's look at an example. So here is an example. So let Rxy be a function which takes two natural numbers as input and outputs another natural number. The rule is that Rp, 1 is equals to R1, P equals to 1 for all P and Q in natural numbers, and Rp plus 1, Q plus 1 is less than or equal to Rp plus 1 Q plus Rp Q plus 1. If this is the case, then can you prove that for all natural numbers P and Q, Rpq is less than P plus Q minus 2, choose P minus 1. So this is the binomial term. So let me just quickly write down here what the binomial term means. In case if I have n and k, this n, we call this one n choose k. Sometimes it is denoted as nck. I will always use the first notation, this notation. So this is n factorial divided by n minus k factorial times k factorial. And what is any number factorial? So n factorial is of course 1 times 2 times 3 till n. So n minus 1 times n. So that is n minus 1 factorial, similarly k factorial and minus k factorial. So the problem asks that, can you prove that Rpq is less than P plus Q minus 2, choose P minus 1. Now as you can see here, there are two different parameters here, namely P and Q. Now which one do you induct on? Or in other words, which one do you use to split up the problem into cases? Now for solving any problem in induction, the basic idea is choose a version of the induction hypothesis or induction version which will help us to solve the inductive step. Number one. And we also have to ensure that the inductive step proves all the cases. Right? So what do I mean by covering all the cases? Till now we had only induction on a particular number, say n, right? So in that case, as I told you again and again, it's basically ensuring that for all the integer values greater than, say, induct on R, and I have to prove that for all n greater than equal to R, PR is true, your Pn is true. How do you do it? You start with the rth state, you somehow ensure that R is true, and then somehow ensure that R plus 1 is true, and somehow ensure that R plus 2 is true, and so on. So one technique is, of course, if R is true, then R plus 1 is true. Then, in other words, if K is true, then K plus 1 is true, then R is true, then R plus 1 is true, then R plus 2 is true, then R plus 3 is true, and so on. Or I can also have things of this much complicated thing like PR is true implies PR plus 3 is true. And if I have the base case that R is true, R plus 1 is true, and R plus 2 is true, then this will say that okay, R is true, therefore R plus 3 is true, R plus 1 is true, therefore, so this is the K actually, so R plus 1 is true, therefore R plus 4 is true, and so on. And you kind of convince yourself that you will be able to fill up all the dots on the right side of R. But now, when I have two parameters, P and Q, it is like instead of the particular N, I have a grid for P and Q, right? So P can be 1, 2, 3, 4, 5 and so on. Q can be 1, 2, 3, 4, 5 and so on. Now I have to somehow come up with a version so that everything else is solved. Let's look at some of the examples. Maybe I can first of all prove that P equals to 1 and Q be anything is true. So P equals to 1 and Q be anything is true. So I managed to prove all these points. Right? And then I will end up proving that if P comma Q is true, then P plus 1 Q is true. And if I can end up proving this statement, then that means that, okay, this is true, 1, 1 is true, therefore 2, 1 is true. 2, 1 is true, therefore 3, 1 is true. 3, 1 is true, therefore 4, 1 is true, and so on. Or similarly, 1, 2 is true, therefore 2, 2 is true. 2, 2 is true, therefore 3, 2 is true. And 3, 2 is true, therefore 4, 2 is true, and so on. So this can be one particular way of ensuring that everything gets filled up. Another way can be that we start with the assumption that all the P1 for 1 comma P is true for all P and Q comma 1 is true for all Q. And maybe then something of the form P comma Q is true implies P plus 1 comma Q plus 1 is true. This can be another of these versions. And note that if I have these dots filling up all the boundary cases, then okay, 1 plus 1 is true, therefore 2 plus 2 comma 2 is true, 2 comma 2 is true, therefore 3 comma 3 is true, and so on. Now 1 comma 2 is true, therefore 1 comma 2, therefore 2 comma 3 is true. 2 comma 1 is true, therefore 3 comma 2 is true, and so on. So in other words, there are various ways again of filling the two-dimensional grid. We have to ensure that we pick a version which fills up the two-dimensional grid. In the case of when you induct on one object, you fill up the real line, the integer line, the natural line. In the case of two-dimensional induction, or when you induct on two things, you fill up the two-dimensional grid. So there are different versions that are available, and we will be going through a few of them. So say the version possibility 1 can be that if you have to prove for all PQ, first prove that 1 comma Q is true, and then assuming that PQ is true, prove that P plus 1 Q is also true. Now when this happens, what is the term that we are going up or going down? In this case, assuming P, we are going to P plus 1. So in this case, we say that we induct on P. Verify for yourself that this particular induction step will indeed prove that, of course, along with this particular base case, will indeed prove that for all PQ, this P of PQ is true. So in other words, the whole of two dimension is covered by this particular induction step. Another possibility is first prove that 1 comma q and p comma 1 is true, and then assuming that p comma q is true, prove that p plus 1 q plus 1 is true. We just looked at this particular case, and in this case what do we induct on? We are inducting on actually both p plus 1 and q plus 1, or p and q, right? So simultaneously we induct on p and q. We are including both p and q. So in this case we induct on p and q. So we push both p and q. Again, convince yourself that this will help us or ensure that this particular version ensures that we cover all the cases or all the two-dimensional cases. Now for version 3, again the same thing, assuming the base case are same, but induction hypothesis now says that prove that this PQ is true for all P and Q such that P plus Q is less than K. And then prove that you can prove it for P prime comma Q prime is true when P prime comma Q prime is K plus 1. So in other words, now here we are inducting on P plus Q. We are saying that if P plus Q is K, then I can use it to prove the case when P plus Q is K plus 1. Again, check that this indeed helps us to cover all the cases or all the two-dimensional points. There is more versions that can be there. For example, we can have this fourth version where we can induct on the minimum of P comma Q. So if the minimum of P comma Q is K, then we can say that okay, I can prove it when minimum of P prime comma Q prime is K plus 1. So here we induct on minimum of P comma Q. So there are quite a number of versions that are available, as long as you can come up with a version where you can ensure that all the points on which we have to prove, so in this case the two-dimensional grid or sometimes the one-dimensional grid or sometimes the three-dimensional grid or something, then we will be through, right? So as long as we can cover all of them, all the necessary cases by this idea, by this inductive step, we should be through. So back to our problem, which version should we apply? So I will be applying the version 3, where the base case is that proof for P1 comma Q and P of P comma 1, it is true, and we induct on P plus Q. That means if I assume that P plus Q equals to K is true, then I can solve it when P plus Q equals to K plus 1, right? So in this problem, clearly the PQ equals to the RPQ. PQ is basically the statement that RPQ is less than or equal to P plus Q minus 2, choose P minus 1. So we have to prove that base case, meaning P1Q and PQ1 is true for all P and Q. We have the induction hypothesis, meaning you have to assume that the PQ case is true as long as P plus K, Q equals less than K, and assuming the induction hypothesis proves that for any P prime comma Q prime is true when P prime comma plus Q prime is equals to K plus 1. So here are the three cases to prove, and again once you get the right version to apply, it should not be a complicated thing to check. Okay, let's see. So the base case, I leave it to you guys to check that the base case indeed holds in this case. Induction hypothesis, we know what we have to assume. And the inductive step is that we have to prove that if P prime plus Q prime equals to K plus 1, prove that the P prime plus comma Q prime case is true. So here, without loss of generality, let us assume that P prime equals to P plus 1 and Q prime equals to Q plus 1 for some P and Q. Positive. Right? P and Q greater than 0. Sorry, P comma Q is greater than 1. Both P and Q is greater than 1. Now, to show that the P plus 1, Q plus 1 holds, it means that I have to prove this thing, that R of P plus 1, Q plus 1 is less than. So this is what we have to prove. So if you put P plus 1, Q plus 1, we get P plus Q, choose P. So this is what we have to show, right? Now, we know that by the recurrence, we know that Rp plus 1 Q plus 1 is less than or equal to Rp plus 1 Q and Rp plus 1. This by the recurrence, by the problem definition. This is in the problem definition. And by induction hypothesis, we know that this is less than this. Why? Because we assume that P prime comma Q prime, P prime plus Q prime equals to K plus 1, or in other words, P plus 1 plus Q plus 1 is K plus 1. So P plus Q plus 1 is equals to K, and we know that by induction hypothesis, as long as this plus this is less than or equal to K, we have the problem, or we know how to solve it. Or that's by the induction hypothesis, right? So this plus this, R of this comma this is less than whatever that is. And similarly, R of P plus 1 comma Q. So plugging these two values up there, we have R P plus 1 Q plus 1 is less than this plus this, which simplifies to this number. So what we have to prove now? All we have to prove is that this quantity is less than this quantity, which is P plus Q choose P. That is all we have to show. So this is what we want to show. And if we can show that, then we will be having the full proof. Now just to complete the algebra here. Now all that we are doing is some algebra. So this plus this, which is what was there in the last slide, the last one, namely this one. Now just to apply some algebra, this one is equal to, I have just unfolded the definition, is P plus 1 minus 1 factorial by Q factorial times P minus 1 factorial and so on. And you can just take out p plus q minus 1 factorial by qp minus 1 factorial times q minus factorial out, and then it gets 1 by p plus 1 by q, and since 1 by p plus 1 by q is p plus q by pq, so p plus q times p plus q minus 1 factorial is indeed p plus q factorial, and similarly p times p minus 1 factorial is p factorial, and q times q minus 1 factorial is q factorial. Thus we have that this one is less than this, which is, by the way, recall that this is actually equals to p plus q. Choose q or choose p, whatever you, both of them are right, and which is what we wanted to prove. Thus we have been able to prove this particular problem using the inductive mathematical induction on two variables. We have seen a number of different versions of induction hypothesis that can be applied. Depending on the problem, one might have to choose the right version to apply. We will continue with our more studies on induction, proof using induction in the next couple of days. Thank you.